Everybody clear on the challenge of designing the SEM and how to make an optimal SEM point? So you have the current coming down to the lens. There's a focus, there's one lens, and these two lenses are basically the condenser lenses. And the critical lens is this lens that does the image, the focus. So in each of these lenses, what you have is you have at each of these points an aperture. And that aperture cuts down the beam. So you see that the beam is going like this, the aperture cuts it down, and then here there's a second aperture here, that's after lens 2. That aperture is the critical aperture, because that is the one that determines the final diameter of the probe. So this aperture here, I had another figure with the apertures, but for some reason that's not here. Let me just see, so that you can see that. Yeah, so that aperture there, literally, I'm trying to write this chapter, but it's way behind. The figures are there, so you can see the figures. So there are the two apertures. It's one aperture here, this aperture here. That aperture is a selectable aperture, and you can change that aperture, the one below lens 2, that allows you to control the final size. Yeah.
Did you say that lens 3 is the critical lens?
Yeah, that is the lens that actually does the characteristics. This lens is very important. So let me go back to the other one and go back to the slide. Then there are these two coils. These are the so-called scan coils. So when you have the beam and you're scanning the beam across the surface, if you just have one coil, what happens is that the beam is deflected along here. And when it goes away from the optic axis, so away from the optical axis, the image characteristics deteriorate. Does anybody know why it deteriorates as you go away from the optic axis?
Probe is going to spread, isn't it?
One aberration becomes dominant when you go away from the optic axis.
Is that stigmatism?
No. No, there's only one left now. That's a spherical aberration. The spherical aberration becomes critical as you go away from the optic axis. So what they do in the scanning is that they do one that deflects this way, another one that deflects this way. So as a result, you can get the same deflection without going away too far from the optic axis. Okay? So that's why you have these two scan coils. And this is a common design attribute in all electron microscopes. You have this in the TEMs, you have them in the SEMs. For the deflection, you don't want to go away. And so here's the optic axis, and again, I think I should have put the other figure here. You have the optic axis and you don't want it to deflect. So what you do is you deflect a little bit with one, deflect with the other one, and you bring it back. So that the deflection is always not too far, and you can still do the scanning across the surface, but you can make sure that the deflection doesn't go too far. There are two deflection coils that are used, and that's the reason we have that. And then of course this is the final lens, and that focuses this one onto the slipper. So the deflection coils, everybody knows how the deflection coils work? They work using magnetic field. Exactly, the right-hand rules, and the simple design of the deflection coil is here. So there it is, you have the coil, you have the deflection, you have a magnetic field like this. You apply the right-hand rule, but the right-hand rule is for positive charges. Remember here, it is a negative charge. So it goes anti your right-hand rule. Correct. So be careful because all these rules are for positive charges. Don't get that mixed up. So you have the common thing, and it always deflects in this plane that I shown here in shape. So deflection is in this plane. And these forces are shown there. There's the beam, there's the current, the magnetic induction, there's the force, then it deflects along. As it moves, instead of moving like this, it starts to deflect like this. Okay, everybody clear on that? That's how these different, yeah.
So just to clarify, you're going to have 4 total pairs of coils, an upper and a lower for X and an upper and a lower for Y to do your full rastering? Okay.
If you want to raster, yeah.
Yeah.
But, well, it depends, the geometry of the rastering can vary. So some, the actual rastering is done in lines, so you go one line, then you step, and then you do another line. So the geometry of this is to make sure that that's possible, because you're really not rastering in the other direction, you're just stepping in the other direction.
Sure.
So you just move a little bit, and then you step and you do a line, you step and then do a line.
But there are two sets of
Exactly.
coils
Yeah,
for each axis.
just so that you understand that the rastering is done in lines.
Okay.
And the current is opposite on each side to focus the beam being
Now, the
closer.
beam is focused by the lenses. This is to only move the beam, to raster the beam, because you have a fine probe and you want to raster it on the surface to get the image.
So for rastering, the current goes the same direction.
The current is all the same, it's just that the beam is just moved a little bit this way because of this Lorentz force. We have already seen, in terms of components, we have already seen the gun. We have already discussed the gun when we talked about sources and probes and so on. Basically, you have a cathode, there is a small potential that's applied, the current comes out of the cathode, and then here's the anode with the high potential, which is, in this case, somewhere between 5 and 30 kiloelectron volts, typically. And then it comes out, and then there is this divergence angle, and that is then controlled by the apertures to make sure that the angular divergence is controlled. Okay, then again, this is again in terms of the gun. What you're trying to do is you're heating your gun, having the electrons come out, and you're modifying the electron, either you're modifying the work function by a potential or a field, or you're providing sufficient energy for the electrons to overcome the work function. So that's the thermionic source, this is the field source, this is something combined field and thermionic source. And we discussed all of this earlier, I just want to make sure you see it again. These are the typical guns that we use. Now, the other important thing in an SEM is this actual detector that you use to actually detect the electrons. And there are 2 sets of electrons that come off the SEM. They have completely different physics. One is what is called the secondary electrons. The other one is the backscattered electron. The secondary electron, what we call the primary or the fast electron that is coming down the column, 20 kiloelectron volts, it interacts with the sample and generates secondary electrons. And we know that the depth at which the secondary electrons come out is only a very shallow depth. So that is a very shallow depth, you get the secondary electrons, and you can create a scanning image either using the secondary electrons or using the backscattered electrons. The secondary electrons have low energy. So your detector needs to attract and grab these low energy electrons and create an image. The backscattered electrons have high energy because they are essentially the same incident electrons being backscattered from the sample. And the backscattering, we will see the variation, but you can imagine that the backscattering really depends on the atomic number. And so there is the contrast that you see. Part of the contrast comes from the topography of the surface, the characteristics of the surface, topography. That's typically what you see in using the secondary electrons. But when you look at the backscattered electrons, you get both contrast from the topography, plus you get contrast from the chemistry of the sample, the composition, the average atomic number. So if you have different elements in different parts of the sample, you will get sensitivity to that on the backscatter. Okay? So you need to detect these electrons. So here's your sample. Here's the incident beam coming in. The B is the backscatter and SE is the secondary. So in order to attract the secondary electrons, they are low energy. So what do? You put a kind of a Faraday cage in front of your detector and put a charge on it. Yeah.
If you use the secondary electrons, can you still get the chemical composition of the sample?
You tell me, can you? What do you think? Good idea, yeah. So you have, so you know the answer. So you see the secondary electrons are coming through, and you have a Faraday cage. Now, if you put a potential of 250 volts in a Faraday cage, these are negatively charged electrons. So even if they are going in some direction, they are all bend over and get detected. More of them can get detected by putting a potential. On the other hand, if you put a minus 50 volts, what will happen? You will repel them. Then you will only detect the backscatter electrons. So you can play with the charge to either attract the secondary electrons, or you can repel them and just collect the backscatter. So that's why the Faraday cage has a mechanism to put a positive and negative charge. Then the main detector is the thing that is called S. Does anybody know what S can represent? Does anybody know how, has seen how the SEM detectors work? It's called a scintillator. And S stands for scintillator. And as you can see, it also has got a small positive charge. It's not quite small, it's 12 kilovolts. So that makes sure that more of the electrons as they come into the Faraday cage goes towards the scintillator and gets detected by the scintillator. What the scintillator does is convert electrons into light. So if you, for each electron, it generates photons inside, and then there is a light guide that takes all the light from the scintillator through the light guide into what is called a photomultiplier. And that is where the signal is processed. After that, it's processed electronically. So this is how a typical SEM detector works. Okay, everybody understands how the detector works? And so it's quite a complicated design. And it's very compact. It sits in a very small space, but it's all of these components are included in the detector.
How does the photomultiplier work?
Well, it basically counts the number of photons, and that's how you need to know at this time. So the number of photons from each electron, when it comes with a certain energy, it generates a certain number of photons, the photons is counted. And there are different ways that the photomultiplier works, but basically it just counts it. Okay, so that's how your detector works.
Can I ask you a question?
Yes, of course, please.
Okay, so you've got varying energies of electrons that are hitting the scintillator. So how does it convert it into light? Because you can't just have it excite and then emit, right?
Okay, so now we're getting into details here. So basically what you have is that for each electron of a certain energy, it produces a certain number of photons.
Okay.
And those number of photons are then discriminated. So there is a complicated sort of electronic circuit that goes with this.
Oh, okay.
So basically from your point of view, what it can detect is the number of electrons that come and hit it and the energy of the electrons.
Okay.
So that's what it can detect. It can detect the number of electrons of a given energy. Okay, so that's as far as the hardware is concerned. The important thing now is the next slide, which is the fundamental sort of physics of what is happening when you have the beam interacting with the sample. This is in a most general case. So you have a beam that is hitting the sample, and you can see it produces a huge number of signals. And either in a TEM or in an SEM, you can detect all of these signals or some of these signals, and you can produce different kinds of information about your sample. So for example, you have incident beam. If you have a thin foil, that incident beam goes through the sample. That's your TEM. So that's transmitted through the sample. You can measure its energy as it's transmitted. And you can create a whole spectroscopy which is called electron energy loss spectroscopy. We already discussed that earlier. Then that beam can be diffracted. So that is in a TEM. We'll talk about this a little bit in the next class or the class after. That gives you diffraction information about the sample. But if you don't have a thin foil, but you have a thick sample, then what you have is you only have the stuff that comes off the surface. Then you have the Auger electrons, the secondary electrons, the backscattered electrons. Then you have ionization of the sample and the deionization process, and then on the de-excitation process you get characteristic X-rays. You can generate light, and that is called cathodoluminescence. Of course, you can also heat up your sample and burn it and so on. If you are interested in that, you can also study that. So those are the signals that you can generate. Now the important thing to recognize is that now those signals have also different presence in terms of depth of the sample. So they're not generated all at the surface, they're generated at different depths. And that's shown on the right side. So here you have this, on the surface you generate the Auger electron up to about 1 or 2 nanometers, you generate the secondary electrons. Then there is this sort of the volume, and we talk a little bit about this electron interaction volume. Then over a certain depth you produce X-rays, and the X-rays can be detected from that. And then the backscattered electron, and then slowly as the electrons slow down, they produce background X-rays, and then their energy becomes the same as the thermal energy, kBT. Then you cannot detect them. So it's important to understand this excitation volume. It's also important to understand that when you have a thin film sample like in a TEM, you are just truncating this excitation volume. So when you have a thin film sample, you are just taking only that little portion, so that beam broadening that you have in the sample is not seen in the TEM, so you get much better spatial resolution in the TEM, because that excitation volume that broadens the probe is truncated by the thin sample. All these ideas clear? These are some of the fundamental ideas of electron microscopy. Okay? All right. So now let's talk a little bit further about two important things that we are interested in. We're interested in the diameter of the probe. So that's what determines the ultimate resolution. Okay? And so here are two simple equations. One is the diameter of the probe. It depends on the current. It depends on the brightness beta. And it depends on the angle alpha, which is the angle of convergence. But as you can see, the optimal size of the probe depends also on the aberration of the lens. So that is, on the right side it is CS, it also depends on the wavelength. So if you change the acceleration voltage, lambda, if you increase the acceleration voltage, what will happen to the wavelength? It reduces. So you can see that by increasing that, you can get better spatial resolution.
What was A and C again?
A are constant. CS is the aberration, spherical aberration correction factor. So let me show you some simple plots. So the first plot says what happens to the probe diameter with the acceleration voltage. This is the effect of lambda. As you increase the acceleration voltage, the probe diameter becomes smaller. Okay? That's because lambda now, as you increase the voltage, lambda becomes smaller. Because lambda becomes smaller, you're able to focus the probe better. Okay, so this is the actual variation based on lambda. The other important thing is that you can see that the optimal probe size, does it increase or decrease with the source brightness? Does the diameter of the probe decrease or increase with the probe brightness? So it gets smaller as it gets brighter. So now if you go from thermionic emission to field emission, the field emission is a brighter source. So you should get an optimal probe, smaller probes with field emission. That's what's shown in the next slide. So you can see the probe diameter and the probe current now. There's a current as well. And you can see as the current increases in the probe, the diameter of the probe becomes larger. So you can see here, as the current increases, the probe diameter increases. That's that expression there. On the other hand, if you go, this is of course the first one where lambda is affected. In the next one, as you can see, as the brightness increases, you get a better, finer probe size. Yes?
What does the P signify? Just the probe?
The D of the probe, but this is the optimal because now they're also including the CS correction and wavelength and all that. So the more critical expression is this D optimal.
What are the units of brightness? Because you have current is I, correct?
Yeah. It's yeah, I can tell you the brightness, but right now I think we just skip it for now.
So more or less counts at this point, or
yeah, the number of electrons per unit area.
Okay.
So how, not the total current, but how the electrons are focused.
Okay.
It's a little bit complicated definition. It will take a bit of time to really define the brightness. But anyway, here we are. Let's do this. Now, the other important thing that also determines the performance of an SEM is what we call the depth of field, which is very important, as we have seen in many optical microscopes. Where we place the sample is important. How much we can move the sample and get the same depth of field. And that is shown in the next slide. The slide also shows some other important parameters. What is called the working distance. That is the distance between the aperture, the final aperture that I said is the critical aperture, and the image plane. Here's your sample surface that is shown here. That is this working distance. The sample is not always at this working distance. It can be moved up and down. Oh, sorry, this image plane can be moved up and down. Now, the diameter of that and this working distance defines this angle, the convergence angle alpha. Right? So that's the diameter that is set by your aperture. You can change the aperture size. You can change the diameter. This is for the lens, the working distance is fixed, and that sets the aperture. Your sample moves over this distance. So here it may be a focal point, but here there is a small finite size. So this thing is called the disk of confusion. And you still need to have an unblurred image over this particular distance that you move your sample. And the way that it is defined is that this depth of field is given by D over tan alpha. D is this sort of, disk of confusion, and this is your final probe on the surface. This angle is defined by the aperture. So by changing the aperture, you can change alpha. So that's how people work around by changing alpha. You change over a smaller aperture, alpha will be smaller. If you change go to a larger aperture, alpha will be larger. But then if you go to a larger aperture, the big problem is you are moving away from the optic axis. You get more distortion. So there's always a trade-off between one and the other to get the right optimal conditions. Okay? And here's a sort of series of images taken with different values of alpha. And so this is different height working distance and different aperture combinations of the same set of samples taken with this. And let me just give you the numbers for these different samples. So the first one is This is the convergence angle is 11.2. The second one is 3.28. The third one is 5.8, and the fourth one is 1.7. So you can see that one is the largest angle, the widest angle. This one is the smallest angle. And you can see that there are different range of, these are all pillars, that there are a different range there. They stay in focus, and some of them stay in focus all the way through, some of them not. And this is what you play with the aperture size and the working distance. Right? Because it's an electronic lens, you can change its focal length by changing the current and the performance.
So is the best one the 5C?
It depends on what you want to see. Which, if you want a large range with somewhat poorer performance, then you would go A. If you want optimal performance to the sort of range that you're working with, you go with C. Now I want to do a little bit of math, which is relevant for all imaging experiments. This is really, really important for all imaging experiments. So let us do what you're looking for in many of them.
I just have a question. So what if you wanted to only look at, let's say, just the roughness at the bottom of the pillars? Which one would you choose?
So you tell me, so if you have a system and you want to look at a very narrow range, you want the depth of field to be small, but you want the performance to be high. Okay. So you want somewhere where you get very good resolution, but a smaller depth of field. Okay. That's what you, and you want parameters, you want to make sure the parameters satisfy that. Delta over tan alpha, you want, that is the depth of field, it can be small, so tan alpha should be large. And therefore, if tan alpha is large, you want to have a larger aperture, but then you have to be careful because once you have a larger aperture, you're going to start having spherical aberration. And that'll start to play. So this is always the trade-off. Yeah. Okay, so now let us do something really useful across all imaging techniques. One of the important things that you want in an imaging technique is contrast. So if you have a flat surface, you want to distinguish one part of the flat surface from the other. In some sense, so we have one part here, another part here. You want to have a difference in intensity I1, I2. If I1 and I2 are the same, you don't have any contrast, right? You don't have any contrast because I1 and I2 are the same. You can't distinguish in your image any difference between the two. So we're going to define contrast, which we call H, is I2 minus I1 divided by I2. This is your contrast. Okay, so that is across the board. Any imaging technique, if you want contrast, you want that difference to be significant with respect to the intensity that you have, whatever signal you do. Now, if it were that simple, life would be easy. What you have now is you're collecting signals, you're collecting counts. There is always a statistical process. So there is some sort of noise on this. And there is also some sort of noise on this. Right? Now, if these noise levels overlap, still you won't see any distinction between these two signals. Right? If one is noisy and the other one's also noisy, the two regions, and the noise is significant, then the two signals will overlap. You will not see a difference between the two. So what you have here, statistically speaking, is that you want to look at this and this. You're looking at 3 sigma 1. That's a standard deviation. And here also you're looking at 3 sigma 2. So strictly speaking, for you to see a difference between the two areas, I1 plus 3 sigma 1 should be smaller than I2 minus 3 sigma 2. Correct? In the sense, this height And so the signal goes from here to here, the signal drops from here to here, they should be resolved separately. Otherwise you don't get a signal. You don't get a good contrast. Yeah? Everybody with me? Okay. Now you can put these two things together. So now let us just write this one slightly differently. So I2 now is equal to I1H plus I1, or I1 into 1 plus H. Yeah, okay, I just took I1H, I2 minus I1, so I just added I1H plus I. So then you put that one for I2 here, so you get I1 into 1 plus H plus 3, sorry, other way around, I1 plus 3 sigma 1 should be less than I1 into 1 plus H minus 3 sigma. And then you can easily show that I1H, when you just take this now, when you add these two together, basically you get I1H is less than 3 sigma 1 plus 3 sigma 2. Oh, sorry, it's greater than or equal to. So then this gives you so that is, and therefore the contrast that you will get, in order for it to be meaningful, should be greater than this divided by I1. Okay, that is the condition that you need in order to have a good technique. Now, if you assume that sigma 1 and sigma 2 are basically the same, then you can simplify that into 6 sigma, and therefore H should be greater or equal to 6 sigma divided by I. So that is the contrast that you need for it to be meaningful for the imaging technique. This is across any kind of imaging technique. It can be optical, it can be electrons, it could be SEMs, and so on. So I can just show it here, since everybody's training their necks. It's all here. So there it is. Those are the two levels. You have the first level, and that is the variation there, and then here's a variation there, and these two should be resolved. And in order to be resolved, this one should be less than this, and then this, and this would be the final condition. And if sigma is the same, this becomes 6, and then I1 or H would be 6 sigma divided by. This is the standard condition that you need for any imaging to have meaningful contrast. And one of the simple things that if you're doing a purely statistical process, if you have a certain number of counts, this is again a very standard thing. If you have a certain number of counts, sigma is typically square root of n. So if you have 100 counts, square root of n is 10. So 3 sigma is 30, that is 30%, right? If you have 10,000 counts, the square root of 10,000 is 100, 3 sigma is 300, and so your 3 sigma is 3%. So the idea would be to get as many counts as you can per second from your, to make this 3 sigma as small as possible.
So you're saying that your noise is related to your number of counts?
Yes. I mean, this is not noise, this is standard deviation, the variation that you will measure.
Okay.
It's not really noise, it's what you measure at each of these points by statistical fluctuations. So a standard method is to use, if I say that I will have, instead of I1, it's just an intensity number per second, sigma is just a square root of I. I is a total for a certain time, that number is, so it's a very good way as a first order to understand how the statistics works. This is something that you should be extremely familiar with. And don't be surprised if you have a question on this thing in the exam. This is a standard thing on all aspects of any kind of imaging technique that requires some sort of contrast. So this is sort of the basics of contrast in any imaging technique. Okay? So you should really understand this very simple mathematical model. Okay. Any questions on this? It's very simple, but it's very important to understand this. So the next thing you need to understand that when you be talking about spatial resolution. So this is actually a Monte Carlo simulation. We have an electron beam. What the electron beam does, it hits, it suffers elastic collisions, then it also suffers inelastic collisions. And for a certain distance, it moves in the forward direction. And then after that distance, it gets sufficiently scattered that it changes direction. That distance is called the diffusion depth. Okay? So the diffusion depth typically is something like that. Then the electron is still continuing to lose energy. And then finally, its energy becomes of the order of kT. Then after that, you cannot distinguish where the electron is because it's just sort of the same energy as kT. And that depth is called the penetration depth.
Are those lines traces of where the electron went?
Yes, these are just Monte Carlo simulations.
Okay.
Yeah. So they simulate the electrons. They calculate some probability of where the electron is going, and then they simulate what happens to the electron on the solid.
Okay.
But this gives you an idea just to see. If I can just show you those circles, you would just think, oh well, but this actual simulations tell you what the trajectory of the electron looks like.
So the penetration depth is then only related to the mean free path in the sample?
Yeah, to some extent it's related to the mean free path. No, it is both the mean free path and the energy of the incident electron and the cross sections.
Okay.
The cross section is related to the mean free path, but also it's a cross section now of inelastic scattering.
Yeah.
So you have to make sure that you have to understand which cross section you're working.
Yeah.
So what I'm trying to distinguish is the difference between the so-called diffusion depth and the penetration depth. At this point, it's no longer possible to distinguish the electrons. They just has the same energy as kT. That is the one that it goes in the forward direction and then it changes direction drastically. Okay? And now there's some plots of what they look like. For this, so there is E less greater than kBT, now it comes to this kBT. So there it is, XD is the diffusion depth, that's the penetration depth. What happens to it as you increase the atomic number? You see the shape of that curve of that volume changes. As you increase the atomic number, the diffusion depth and the penetration depth decrease. And also, it becomes squashed, it becomes a little flatter. And then, if you go to increasing beam energy, the same thing, it becomes a bit longer because now the energy, the beam has more energy, it can penetrate more. And there you have the diffusion depth, the penetration depth changes, and then again it becomes a bit longer, but then you have the effect of it. So both the atomic number of the sample and the beam energy affects the diffusion depth and the penetration depth. These are based also on Monte Carlo simulations. But I'm only showing you the actual volumes. So when you use SEMs and so on, you have to understand these conceptual ideas to optimize what you're looking for. Okay? Any questions up to this point? So, this we have seen this slide before. So when you have electrons with different energies, you have various excitations, but the most important thing that we're looking at are the secondary electrons and the backscattered. The secondary electrons are here, and the backscattered electrons have the same energy as here. This is in transmission, but the backscattered electrons have the same energy as your incident wave. Coming back, the same energy. People have done a lot of simulations of the energy of the secondary electrons, and they typically look like this. They have small energies, 2.5 volts, and they come back, and the one in black is the simulation, and the one in red is actually experimental measurement. So you can see these theories are pretty good that they can predict. That's for copper, that is for silicon. You see the secondary electrons come back with pretty small energy, about 2.5 electron volts, and they're coming just from the surface. And then the width of these peaks is 9.1, so they are pretty good. The models are pretty good. The theoretical models can predict. So this is why you put this very high voltage in the Faraday cage to attract these electrons.
What does the width of the peak tell us again?
It just says that, so the energy of, so this two, well, it just says that it's a statistical process, so that typically what is happening is that it has this range of energies, and it will also tell you the sort of depth over which the secondary electrons are coming as well.
Okay.
But the peak tells you that they're mainly coming to the surface. There may be a smaller one that comes from a little bit further depth of the sample. And it changes with the atomic number. As you can see, this is copper, that is silicon. You can see these models. So, then here is the incident electron energy and the secondary electron yield. As you can see, that as you change the incident energy, the yield goes up, but then it starts to go down. Can anybody give a physical idea why this is happening? Take a guess.
After a certain energy threshold, there's not going to move anymore?
No. I mean, you're sort of heading in the right direction. So, if you have higher energy, we said the penetration depth is large, goes deeper. But secondary electrons always have a small energy. So, as you go more and more, the secondary electrons don't come out. Or only from the surface they come out as you go down. So, there is an optimal voltage. Above that, it starts to go.
They get trapped kind of like this.
Yeah, they don't come out. They just get trapped. They dissipate in other mechanisms. So, that's why you have this peak. So, the secondary electron depends on, of course, primarily the work function. We already know that. You have to get it out of the solid. So it depends on the work function. It depends on the beam energy. And you can see this is the beam energy and the total beam current. And the overall density of the specimen. That's why we saw a difference between the copper and the silicon. Okay, so that's, see, these are things that you should understand, that the secondary electrons depend on these various conductors. Now, there's two important things that happens in terms of the secondary electron generation. As we have said, it depends on the topography. That's how we are able to make the topographical images of what the surface looks like. And also there is something called the number contrast. So the topography is in, for example, as you can see, you have a certain beam, just like you have in oblique incidence in the optical microscope. The topography will allow you to will generate different amount of electrons in the direction of the detector. So that the detector is placed here, and if the sample is tilted towards the detector, more of these will come. So if the sample has different orientation, then the topography will detect the amount of detectors. That's one. The second one is what is called the number contrast. The number contrast is that when you have sharp edges like this, the the secondary electron generated here, even at a certain depth, can come out because there is only a certain sample depth around. On the other hand, if you are somewhere here, for example, if you go down a little bit thicker, it cannot come out. So you get contrast by both mechanisms. The topography, which is the orientation of the surface, and a number contrast coming from sharpness of the edges and so on, where even when you get excitation at a certain depth, the surface is really close by, and you still get the secondary contrast. To overcome some of this that's why we do this. We do this sort of thing where we try to take the secondary electrons by applying the potential to make sure we can still collect many of these. Even though they go in this direction, we try to bend them towards it by applying the potential. So you get two mechanisms of contrast. One is the topography, and the other one is the number contrast. That's why we can get these reasonably good images. So here is an example of this. These are some sort of ceramics. You have fracture, and you can look at these at different resolution. You can get various contrasts from various surfaces, various orientations, and so on. Okay, I will talk about this and show you one more here, and then the next class we'll talk about backscattering, and then we'll compare the backscattered electron with the secondary electron. Okay? Your homework, everybody got homework 6? I should be due